for everything running 5 minutes late today. In fact, oh, well, yes, just under 5 minutes late. But we'll give you the 5 minutes back at the end. So
Okay.
David, the
Yeah,
floor
but lunch is short, so okay. All right. Well, good morning, everyone. And like everyone else, I'd like to thank the organisers for having me here today, and all you all for attending the talk. These are my favourite kinds of meetings, where we have different people, different backgrounds, different problems, and good ideas. So congratulations to the organisers. A small note of interest, looking through the schedule, is I think it's the first time in my whole career I've been to a meeting in energy with almost perfect gender balance with the speakers. It's about perfectly even. So, and today's 3-3. Tuesday was, I think the girls won 4-2. So things have changed, Maria. I'm sure you'll agree, from years ago. Okay, well,
we are reversing the time. We are going back.
Yeah. Okay, well, it's a change of pace back to system dynamics, and the talk will pick up in the spirit of Janusz, where is he? Here. That it's an old topic. System dynamics and equations like swing equations have been around for a long time, but I'd like to try and show mathematicians and younger theoreticians that there's still good life in these topics. So my talk is not really aimed at people like Janusz and Maria. This is sort of old, maybe some history. But I'd like to show you that the interaction between mathematics and energy is actually a very old topic around dynamics. In fact, nearly 100 years old. Okay. It's mainly a talk about mathematics, and it's kind of personal. I did undergraduate degrees in maths and engineering, and I did a PhD in systems theory, and so there was absolutely nothing useful until I did a postdoc at Berkeley, and they had money in the systems engineering for power program, and I got interested in power problems and sort of stayed with them since. But there is a bit of a story about maths and energy there. But contrary to my early thoughts and prejudices, more recently I've come to appreciate, as Shmuel expressed the other day, that really we're underplaying computation, and partly because it's trendy and partly because students like it and so on, I've even got interested in database methods. So depending on how much time I run, people my age always have too many slides when we start talking sort of generally. I'll try and give some thoughts about the relative merits of these different approaches. What am I interested in lately? Mostly, I'm very interested, like a couple of other people in the room, about how the role of topology of grids influences almost everything, okay? Whether it's from an OPF to a stability analysis, the topology of the grid plays a big role. If you talk to practical people, this is, I give a lecture in Australia called Power System Modelling in 3 hours. It's for people who are outside the power engineering area, and I always show this slide. Practical people have one system, and they're super concerned about all the dynamics of that one system. So I'm, as a scientist, you might say, I'm a bit outside that box. I'm interested in lots of different systems and how the structures affect what goes on with the dynamics. We can simplify the dynamics into angles, frequencies, and voltages, and my emphasis throughout this talk is going to be to tell a story around the first problem, which has much greater universal appeal, and that is that a power system is just a large synchronous system, which gets you into physics and mathematics and other areas. Okay, we all have seen this picture of the dire consequences of getting it wrong, and we all know the story about what's new. Controllable generations becoming more random, random loads becoming more controllable, etc. My point is that all this creates a whole new era of dynamics problems. We can just talk about the dynamics of converters and loads and so on. It's all, there's a lot of new issues, so much so that the IEEE is going back to revise all its stability definitions to accommodate these new things. Okay, my own activities. I'm not going to dwell on this. I live a busy life, although I'm supposed to be retired by now, in two centres, one in Hong Kong and one in Sydney. The bigger job is in Sydney, in Hong Kong. And we have about 80 people in the power area, including a large power electronics group, one of the best in the world. And that has good benefits because power grids and power electronics are getting more and more intermeshed now. So we in our big projects, we've benefited from that a lot. In Sydney, the focus was around a large project that we had, just to link with the current workshop. We had a large project, 13 million Australian dollar, about 10 million US, which was aimed at what will the Australian grid look like in 2050. Now, if we could take politicians out of the story, I could give you they'd probably give you a good answer, but the politicians are there, so it really gets into a lot of scenario analysis and so on. Anyway, so we have a lot of things going on in these two groups that relate to maths, but like I said, I'm just going to focus on this one aspect of transient stability. So let me skip ahead. I'm talking as if I'm talking to people who have different sort of views of the energy picture. The thing and many things are a bit of a surprise. The one thing is, I think Stephen Lowe first said this to me, is this one big machine aspect of the power grid. In actual fact, the power grid is, I call it granular or hierarchical, you can say. These days, because of all the changes, we used to, at least the theoretical types, we all used to sort of focus up here on the high voltage grid. And we used to make assumptions about what everything below that level did. In particular, we had things called like load models, which were very dubious in some cases. These days, because of the demand for the things that are being talked about in the other talks, you've got this one big machine where like nodes in the bigger network are themselves a network, and you can even add households down here. So this is where I have to educate power electronics people, because they're talking about devices down here at kilowatts, and up here is gigawatts. And that scale from kilowatts, to up through megawatts to gigawatts really changes how we need the paradigms that we need to use. But we are now doing stability analysis and control across that, one big machine with all those layers. Okay, the approach we take, as I've been influenced from my days in California and before, and also my control theory background, is I don't need to say this in this audience, but we always value the sciences, like the control theory, the stability theory, network science. I need to value that with some qualification, but optimization, game theory, all these things are part of, and that's what makes it such an interesting subject. And we do theory, we do computation, although I agree with Shmuel, maybe we need more of the computer science type, if that's what he meant, of computation, and of course we do lots of algorithms. Okay, let me move on. The mathematics. First point, I don't have time to do a detailed history. I sometimes give a talk called Power Network Science. It's to say that network science is not immediately applicable to power systems, but there is a power network science. And it started, you can talk to Göran Andersson, he might say it started in Sweden in the 1920s, I'm not sure. But you have to go back to early days in Russia when Janusz has heard, we've talked about this, that was it Lenin said communism equals Soviets plus electricity. So electrification. So the power grid was a major part of nation building, and a lot of powerful scientists got involved in it. And these guys could do maths, okay? So, and then the history goes through stability analysis, and the US got involved there. When I was young, it was all stability analysis and dynamics and so on. And then a big boost came in the 80s with this systems engineering for power program, and that brought in a lot of people from outside. So Maria came from a famous systems theory, you were a systems theory school, right, or mathematics school in Washington under Zaborski, Bailey at Boston, Wu and Varaya at Berkeley. They're all highly theoretical people. And I was a postdoc of that era, and so on. And then there was two missing decades, although some of you sort of kept at it, and under some kind of broad banner like smart grids, you might say, there's a whole lot of new things going on. And of course I'm nervous mentioning names here because I'll leave people out, but now we have quite a flourish of activity theoretically. Funding, I'm not sure in the future, but anyway, it's an old topic with a good tradition for using mathematics. Okay, so let me come to the topic of what is complexity. This one big machine is highly nonlinear, highly interconnected, granular, as I said, kilowatts to gigawatts, heaps of uncertainty, which many people have been discussing, and hybrid. So if you're a control theoretician, that's about everything you could wish to make the problem difficult. But to go back to something concrete, my benchmark for talking to people about energy is, I said the other day, is that I just like to appreciate that they know what the power flow equations are. If we all agree on that, then we can sort of go from there. But okay, if you look more closely at these equations, they're highly nonlinear, very, and lots of mathematics has been thrown at those equations going back to, well, probably earlier, but certainly in the 80s, Bailey and Burns and people like that, and people at Berkeley got involved. Now there's a new era, more emphasis on solving them. Okay, somebody said, I think it was John said, control theorists always draw block diagrams. Power systems people always draw one-line diagrams like this. So this is a very simple one with 3 generators and a big load. And just to emphasize the nonlinearity, this is a picture from Ian Hiskin's thesis, where he released one of the generators, and this is the manifold of solutions of plotted against the reactive power. So you can see, depending on that bus power, you get 0 solutions, 2 solutions, 4 solutions, etc. So that's pretty nonlinear. So, and the situation these days is more complicated. So I've totally lost interest pretty much in linearized models. But I mean, go ahead, they can be useful, but in my emphasis is to get away from linearized models. It's okay to use them to talk, as long as you're aware that you're talking about just one point in a very complex situation. This is one of my favorite examples for toy power systems, and it comes from a guy in California, I believe, Corsac. I believe it's, maybe Shmuel knows better, but I believe it's motivated by the Western grid of the US. And it's a simple toy power system, and the interesting thing about it is that it has 2 stable solutions of the power flow, meaning stable, dynamically stable solutions. So, and it's the same structure, and it obviously relates somewhat to the ring structure, but it also relates very strongly to the behavior of power flow. So I'm not saying it's a counterexample to some network science, but I'm saying it makes the idea that we can say a lot just from the connectivity a bit dubious, because this interaction between the structure and the power flow is very strong. And if we're going to do theory, we just need to account for that. All right, the problem we're discussing is synchronism, and synchronism for power grids is not the same as synchronism in physics and biology. All the generators won't come perfectly together, because if they did, there'd be no power flow on the grid, which means there's no point having a grid. What you get is some kind of bounded synchronization, where all the angles of the generators have to sort of flow in a tube, okay, and stay close enough together. This is bad, this is okay. And I'm going to base the talk around a very simple model. This model, which is commonly used by people these days, was invented by Art Bergen and myself just as a trick. So just to talk about mathematics, it was just a trick to get a Lyapunov function. And then we kind of lost interest in it because it was too simple. Now it's all over the place. But that's an interesting story about. Anyway, the model is very simple. It's a swing equation with a real power flow equation and an identification of the load in the grid, okay, as a simple first order differential equation, and the synchronism property is well known. Okay, but that model was not the common model. There was a classical model, which I can just illustrate quickly. If you take this 4-bus system, what the classical model did that everyone else was using was do a network reduction, and then you ended up with a network just between generators. If you want to read the whole story about Cron reduction, there's no better place to go than Florian's and Francesco's paper here. But the reduction is a very common thing. It's in all textbooks, right? Just the process of reducing. The issue was that you took a grid with some real loads and maybe lossless, and you turned it into a network which was lossy because of the loads. And this is the classical model with these transfer conductances that came from the loads. So my first job at Berkeley as a mathematics background, stability theory background, was to try and get a rigorous Lyapunov function. And I think I would have still been trying, except for Art Bergen saying, well, why do we have to do this reduction? Why don't we just keep the loads? So simple. So after that, the mathematics was actually quite straightforward. We had a rigorous Lyapunov function and so on. So that was a lesson. A lesson to me. I'm trying to climb this huge mountain with every bit of mathematics I know, and a simple suggestion about modeling just cleared the way, and we got a nice answer. Okay, so just to remind you, there are formal definitions of power system stability which relate quite well to the mathematical definitions, thanks to the involvement of some analysts like myself and Joran and Claudio, others, Alex. Maria will remember there were lots of debates about these definitions, and but the definitions as they stand relate quite well to stability theory, so we can use Lyapunov methods. For those of you who know about them, this is about finding energy-like functions which are positive and reducing along trajectories. And a good book in that area is by Xiaodong Chung, who was a student at Berkeley just after I left. So that's bringing all that machinery to power systems really flourished, but not with that simple model that I just showed you. That got discarded quite quickly because it has major disadvantages. The voltages are fixed, and the load model didn't quite relate to things we knew about. It was convenient, but we quickly got into the business of, okay, let me just say, the classical model, the way they tried to solve that was just to assume these transfer conductances were zero or small, which is ridiculous because that's like saying there's no loads in the system. But still, papers were written around all that theory. And when in actual fact, the only rigorous result that I knew of anyway was for small systems. With the network preserving model, there was no transfer conductance problem, and this is just an extract from the paper. We could prove a rigorous Lyapunov function. Moreover, we could say things like the terms in the Lyapunov function related to physical devices, but we didn't really play on that too much. It was just like a nice thing to mention. The reviewers criticized the paper for increasing the dimension of the system, and the usual hassle with getting past reviewers. And I argued, but hang on, it's a sparse system, blah, blah. But we got there in the end. So, but, like I said, we just moved past it quickly. We wanted to put voltages in the system. We wanted to get better, different load models. And so Ian's thesis was around getting differential algebraic models. The problem there was no Lyapunov theory for differential algebraic models. So even Mariels and I did one. We took a step sideways and put on our mathematical hats, and we wrote a paper about Lyapunov theory for differential algebraic systems. The interesting thing there is that the Lyapunov functions are not single sheets. You get these sort of, because of the multiple solutions of the algebraic equations, you get these multiple energy sheets picture. Really nice picture, but it's kind of not gone anywhere because it's not very practical, but we had some nice theoretical analysis of these systems. And we had Lyapunov functions. Now, here's my lesson number 2. I took a trip to Russia and I'm sitting in Vladimir Stroyev's kitchen and he tells me about a result by a guy called Vasin in St. Petersburg years ago, 10 years before our work, where he didn't have everything that we had with Lyapunov theory of differential algebraic systems, but he did have a first integral of something like the structure preserving model. So my lesson number 2 is make sure you know what the Russians had done before you start doing theory. Okay, but there are incompletely solved problems here. The issue of voltage dependent, okay, we got past the transfer conductances, but the voltage dependent real loads, there's still not a really good solution to that. There are some papers written, but you'll sort of see that they make strong assumptions. I've talked to people in mechanics, so one of my hopes when I come to meetings like this that there'll be somebody in the room who knows mechanics who'll say, I know how to fix that, but it's never happened yet. But that's a serious problem. And I'll just mention later that it's come back to be a much more serious problem recently, because we can fudge around it with algorithms and numerical methods. But when we come to the stability theory of microgrids, the transfer conductances are serious. You cannot ignore them. And I don't know, Florian, but I don't think there's a good solution to that stability problem yet. So I think there's good problems here still. Okay, some points. I think I'll move past this. Okay, this is just the stability theory of differential algebraic systems have their own points of interest, and one of them is these multiple, this is once again a picture from Ian Hiskin's thesis, have these points of interest which some of you might like to pick up on. But this was also an era when, like when I was in Newcastle studying stability theory, half the class in some of the maths classes were the electrical engineering students. We were studying functional analysis, we were studying differential equations. And then I went to Berkeley and the students are over in, I said the wrong place to somebody yesterday, I think it's called Evans Hall. And they were taking courses from Steve Smile and Mo Hirsch and mathematicians about differential geometry. And so there's heaps of papers out of the Berkeley school related to bifurcation theory, chaos, stability. They went into more detailed models of the power grids with more detailed generator models. This is under like Varaya and Wu and students and Xiaodong Chang and so on. So lots of real mathematics was going on there around these dynamic problems. And then whatever happened, it sort of died a bit. That's probably when Felix came to Hong Kong, I don't know. But there was, as we had a review paper recently, Florian was part of that, and we made some points about where all this stability analysis sort of falls short of today's concerns. So for a start, the stability properties, with a classic split of voltage, angle, frequency stability, maybe doesn't work quite so well in some situations today. The whole role of grid structure, the load dynamics, the load's now different. The big thing we struck when we did the future grid project was, oh, we'll just use load forecasting. Well, hang on. We're doing scenarios on the pickup of EVs and demand response, and all that changes the loads. So the whole subject of load modeling as like a separate exercise is dubious now, okay? It's part of the story. It's this one big machine thing. And then not to mention the power electronic dynamics. Pretty much everything in the IEEE definitions paper is for timescales which don't include power electronics. So if you want to get some insights to what we think about, you know, things needing more work, you could have a look at this PSSC review. Okay, then comes, I'd sort of put power systems aside some years ago, and I was a head of department in a school in Hong Kong, and my neighbour was Guanrong Chen, or his English name Ron Chen, and I was going to his seminars, and it was all about graphs and but synchronization of chaos, nothing practical except maybe something in secure communications. But he had all these results on synchronous systems. And I thought, well, that's interesting. These guys are putting all the emphasis on graphs, and in power systems, we put all the emphasis on dynamics. So he and I wrote this little thought piece about it. And I sort of underestimated the subject a bit and just kind of left it at that for a while because I was doing other things. But I'll come back to that story later. But now, to move forward a little bit, I'm seeing some new directions. First of all, in my own work, I'm questioning the, well, first of all, let me come back, sorry. This first point here sort of epitomizes the network science view. And that is, a system has synchronism if you get the right interaction between the node dynamics, the connectivity of the graph, and the coupling strength. And there was nothing like that in the theory of power systems at that point. But it's a very simplified result, but it sort of was really tantalizing. And also when you look in the physics and the biology literature about synchronizing, they also had like related ideas for like emergence phenomena in these networks. So I really got a bit excited about that and spent about 4 or 5 years just studying dynamic networks, thinking, oh, one day I better come back and look at power systems. But by then, Florian had taken off with his papers on the subject, and I could see that it was really an interesting area. The first thing I think is that there's a change. The old paradigm was what I call equilibrium event equilibrium. We're in equilibrium, we get an event, and we ask the question, do we come back to the equilibrium? There's many situations now where the idea of an equilibrium is really questioned. As Lena showed in her talk and other talks here, we've got all this movement in generation and loads. The situations where the system's nicely settled in an equilibrium are less common these days. So maybe the synchronism view, where you're looking at a system in constant disruption but just trying to keep it all together, is a stronger theoretical paradigm. The influence of grid structure, and then the greater penetration of converter integrated generation. Is that what that means? Different timescales, as I said, new problems. So I don't have time to go through details. I'm just trying to impress maybe mathematicians and younger people here that there's things going on that are interesting. But we picked up on Florian and other people's work, and I thought, well, this looks like interesting. Maybe I should go back to my old model and see what we can do. So we just now. The model we use of a power grid is not differential algebraic systems anymore, but it's dynamics on graphs. And you've seen enough of that to kind of understand what it might be. The transmission lines are links, the generator and load dynamics are nodes, but none of the network science is applicable because it usually assumes the node dynamics are the same, very highly simplified assumptions like that. But there's some papers here. Florian's many papers. My own, I have a really nice team in Hong Kong with Ye Song, who just finished his thesis with about 6 papers, and Tao Lu was my student in control theory, but I've converted into a power guy now. And so we're doing, many of these papers have already appeared. And Li Jun Zhu and I wrote a paper in SIAM and there's another, I thought I mentioned Florian's paper by SIAM too. So the papers are appearing in networks type engineering journals, some are in physics journals, and some are in SIAM, and some are in TAC. Okay, but this is where I think I may have made life hard for myself. Dilson, I don't know if he's here, but these guys in network science are writing papers in in Nature and these journals about power systems. And they take the simple dynamics and turn it into a Laplacian and compare structure preserving models with this is what happens when you do the network reduction, and it's quite interesting. You take a network with 678 nodes and 822 lines, and when you do the network reduction, you end up with an all-to-all network with 170 nodes, but like 14,000 lines or something. So it's kind of interesting, but I'm thinking, hey, if these guys can get papers in Nature with that analysis, we really made life hard for ourselves trying to do Lyapunov theory of differential algebraic equations and so on. But I joined the effort. So we started working. Well, the first thing that was really good luck was that these guys showed that our model actually, for free, includes a very simplified model of renewable power. That load model can be interpreted as a simple load model, or it can be interpreted as a generator with zero inertia. So for free, we get a simplified model which includes the dynamics of conventional generators and converter-fed, Druck-controlled renewable generation. So that was convenient. Now, this puts aside the issue of faster time scales and so on. But anyway, so we started work, and I'm just going to skim across this with formulating our own versions of Laplacian matrices in terms of the power flow, and came up with new theorems on relating the behavior of the Laplacian matrix with stability analysis. But some of this was known, but what we're able to do is dig into the Laplacian matrix now and get new insights in the role of what we call critical lines on stability. So there's a number of new theorems which fell out. Most recently, we've been studying what we call effective resistance properties. It's like electrical distance in the grids through the Laplacian and how those relate to stability. I don't really have time to tell you details, but we've gone back to the old model and with this network science viewpoint shown that we can do more detailed analysis than existed already. So the general ideas are the Laplacian matrix, weighted Laplacian matrices are known things, but now the weights relate to power flow, provides information on stability. We get line-based stability criteria now, so digging into the structure of the graph, we can show that small disturbance unstable if and only if relates to critical lines on cut sets. If the critical lines don't form a cut set, you can analyze it through an LMI. And we have this recent paper submitted which extends the earlier paper on the role of these effective resistance properties which you sort of pull out of the Laplacian. There's another paper which went back to the classic problem of transient stability, and in Songye's thesis he came up with some new graph, well we came up with some new graph theory which relates cut sets to loops, and just got stuck into that graph theory can play a big role here, and actually found some new insights to transient stability, and then came up with an index to measure, so that you can look at the system network and analyze cut sets in terms of these indices to show the inclination of the grid to separate along those cut sets in a dynamic situation. And we had a version of that in the old paper, but in Songye's thesis he's done a much more precise version. Okay, like I said, the stability paradigm has kind of shifted from this equilibrium event, Lyapunov thing, to a continuously disturbed synchronism. And we still bring mathematics tools into this, ISS stability, some energy function ideas are still relevant, but now in this sort of new paradigm that we've been using. So I don't want to dwell on details, but yeah, here are the two Siam papers that you should read. One, Florian's, and then ours. So this is with the very simple model. So I shudder to think what this would look like if you went to the more detailed differential algebraic model, but maybe somebody else can do that. So we just have the usual sorts of definitions for phase cohesiveness, frequency boundedness, for synchronization, and then the model, that this is still the, you know, that simple network preserving model, but framed in a synchronism framework. We're not thinking equilibria here. This is a continuously disturbed system. And trust me, that looks terrible, I know, but trust me, that is the power systems version of that simple coupling greater than d over lambda 2. I mean, the Laplacian is in there, and so it tells a story about the interaction between dynamics and network and coupling. But of course, it's got quite a lot of detail to it. All right, so this up to now, I can say that the graph theory approach has brought new life or new insights to old problems, transient stability problems, small disturbance problem, and we have results coming on voltage stability too. But this graph-based approach kind of can take you into new things, which is nice. So I just mentioned two. Once again, Yesong thesis, I think this is one of the first results on like distributed stability analysis, where you have it's microgrid context, and the idea, a lot of our work is also distributed control. So he got some ideas from Lu Tao and so on. But the idea is that if you have a certain amount of communication possible in the grid, you can actually pull all that together to do a stability analysis of the whole grid. The problem with traditional stability analysis and the one big machine idea is that you've got to kind of model the whole thing, and it just scales up. Any test that you want to do for stability just gets bigger and bigger and bigger. So people have been asking for years, is there going to be some way that we can do this in a more distributed way? One term that I heard a control theorist use is certificates. If we can sort of check certificates around the system, can we get an overall stability assessment out of ticking certificates? Well, this is in the direction of that. So with limited communication, one node has to collect things, but in a few steps, that node, you can get an overall assessment of the stability of the system in a distributed way. So that's one result, and the paper's in a special issue. But I think this is even cuter in a way. I like this result because, the next one, because it came from the power electronics people. Ron Hoy, who's our star electronics professor, he came up with this device called electric spring. He calls it the Hooke's law of electricity. And the device includes demand response and voltage control, and can even include frequency control. I think of it as just a smart load, a smart controller. But anyway, these guys are in the lab building these things. They're not theoreticians. So then they found that if they put all these electric springs along in a cascade, the stability got worse. I mean, as a physical, this was stability in terms of physical devices. So I said, yeah, come on, we can do something with this. So we modeled it in an abstract way, and we could pull the earlier framework out, and we came up with this, that the algebraic connectivity of these radial systems, the algebraic connectivity actually goes to 0 if you've got a node where you relate the connectivity of that node to the total number of nodes. If that starts getting small, in other words, you just keep adding things without meshes and so on, then the algebraic connectivity goes towards 0. And this is a major factor in stability. So then the second result is if the eigenvalue of the system dynamic Jacobian approaches 0, if the algebraic connectivity approaches 0. So this is set up to say that just kind of adding things in radial systems with is going to cause stability issues, and it purely relates to the structure of the system. And I'm probably running out of time here, but you know, we've done these toy studies of which show that if you just keep adding things like this, the system gets less and less stable, but as soon as you make a mesh near the ends, then the stability comes back again. So I kind of like this interplay between structure and stability, but it really sets off a whole lot of questions about how this relates to bigger systems and pieces of the system, how they're, you know, are connected together. Okay, I'm going to skip over this. The second big problem in my life for stability analysis was this one in Sweden, a voltage collapse. And I got a lesson that we had, as a theoretician, this was a bigger problem. The problem was we didn't even have a model for this. What we thought we had a model for transient stability, it turns out it wasn't a good one, and we changed it. In this case, we had no idea. So I went and talked to a guy in industry who I would claim knew zero mathematics, but he knew physics. He knew the physical behavior of the grid, and as soon as I talked to him, bingo, I went back, wrote down an equation, and we could work all the analysis out. But so that's my lesson for theoreticians. Don't be scared to talk to people who don't know any maths at all if you are trying to solve a new kind of practical problem. Anyway, so we ended up with a new set of differential algebraic equations and a whole lot of analysis and stuff to go with that. Okay, but now we're coming back to it, trying to get this graph theory picture in there, and we read John here, Simpson-Porco, his paper, and with Florian, but I think this is in a very preliminary situation. The problem when you put voltages in the picture is you sort of kind of get two graphs in the dynamics, and it's more complicated. But anyway, we will press on and see what we can do with that. Also, for voltage stability, the state of play of Lyapunov functions is not real good. So I'm a bit excited about something Maria was talking about the other day, that maybe there's a hope in all that. Okay, just to impress you that I think for you young theoretical types, I think this is a subject that's had a long history, and there's still some interesting problems, such as I think I've mentioned a lot of these things, so I won't dwell on it. Okay, I'll just try and quickly say something about computation and database methods. The project in Australia that I got involved in was, what will the grid look like in 2050? We had economists, we had energy types who predict the price of gas and stuff out, you know, into the long distance future. We had planning people, and we had moi, which is dynamics. Now, that was already a little bit imaginative, because normally in Australia when they start talking about future grids, dynamics is just not mentioned. It's like, whatever the economists do is going to work. Well, sorry to the economists, but you do need, what we talk about, the energy trilemma. We try and get low prices, high security, and low emissions. And that involves an interaction of, it's by nature interdisciplinary. The security aspect is a lot of what we're talking about here. So I'm not going to dwell on this, but they had this industry forum. People projected into the future about fuel prices and policy and blah, blah, and blah, blah. And they came up with a lot of different meta scenarios. And then they handed a bunch of academics, including me, 13 million Australian dollars to kind of analyse all this. And I've already mentioned this. So we got the first problem is we didn't really have a good model of the Australian grid, because it's now all in different companies, and getting a model of the Australian grid was actually, well, we basically gave up. We had to make our own out of things that we could find. Since then, one of my students in Hong Kong has spent a whole year now constructing, but just a static model, because there is a lot of publicly available data. But that is a big issue. But just to show you this one slide, I think, which is in a recent paper, it's already appeared. we took a totally different approach. It just kind of, all my previous ways of thinking went out the door with all these different scenarios, and that's what these things mean here. We sort of coded scenarios in terms of uptake of storage, uptake of solar, household solar, uptake, you know, we sort of coded all these scenarios. So you end up with so when you take the 8,000 hours of a day and all the renewable power and all these different scenarios, the idea of the up and off analysis is a joke. So it was a computational problem. Problem was, my students, if they wanted this is the study of the rock-off frequency change through all these scenarios against the uptake of non-synchronous generation. The students would set the algorithm going and come back next week, okay? It was just such a massive amount of computation. So we didn't have the resources to buy a supercomputer, but as Shmuel said the other day, they should be doing this. Well, I think that's what you said. This sort of big computation of all these scenarios out into the future, surely an industry so rich can afford a few $1 million to run this kind of computation. And you can see for the Australian grid, we have this extreme debate where the Conservatives say coal is everything and we should have done nuclear years ago, and then we have the Liberals saying that it should all be 100% renewable. And I'm saying in the middle that I'm agnostic. I want to see the maths show me what works. Well, for this model, and for nothing really special in terms of demand response, we see a definite kick around 60 to 70% integration of renewables. Now, I don't want you to take that seriously because of the modelling assumptions made. But I think in principle, any grid in the world will have some kind of story like this. Maybe this figure's 80%, 90%, I don't know. But we shouldn't assume 100% works, and we shouldn't, you know, let people with no imagination say we have no renewables. But so this is a computation story, and I got started with it. I don't think I'll do any more on it, but it gave me a new appreciation of Monte Carlo sampling and simulation, but it all has to be done scientifically, of course, not just random type simulation. And yeah, we've got a paper submitted where we present, you know, scenarios, and this is a kind of pictorial representation of the level of stability problems at different places in the grid going out into the future, but I don't have time to dwell on it. Okay, but then alongside this, the 100% renewable system question is interesting, theoretically. So one of my students is looking at that now, and it's motivated by this paper by Vijay Vittal, where they did a study on the WECC system. And so she's looking at synthetic grids and the sort of models that, you know, converter-fed models. And she's also including, we've got some work going on with new load modelling, including the effects of PV and energy storage, so we've put that in there too. And she's coming at, once again, this is kind of computation, how for different systems with different levels of integration, how, and now we're using Songya's cut-set stability index, just how stability will vary with these different, I guess you can say, scenarios for integration and network structure. This is kind of early days for that. So we have this computation work going on alongside, hopefully, some theoretical work. The database thing, I've only got a couple of minutes. If we review the situation of all this history of stability analysis, it's a bit disappointing. The energy function methods, I could upset people with these comments, but it was interesting, but I don't think you'd say it's widely deployed now. So I know, but the one thing that I do know is very widely deployed is actually a very simple method by, it started off with Yusheng She and Mania Pavella, which is called the extended equal area criterion. And Yusheng She does contingency analysis of the whole Chinese grid with, you know, thousands of contingencies and so on across such a huge grid. It does it in just like a few minutes. So they depend on that. These days, I don't really see that as an energy function method. It's actually a simulation database method where he uses the extended equal area criterion as what you might call an indicator in the midst of all this simulation and data collection. So you could regard that as anticipating more data-based methods, you might say. Now, let me just say, yeah, this is my current picture with a few students. I stole this picture from Miranda, who gave a talk in Hong Kong. The idea is we still need methods for fast stability analysis. We can't wait, although Yusheng seems to get away with it, we can't wait for long simulations to decide what we should have done back here. So in my control theory work, I did some stuff towards what we call human-like control, and that is a kind of learning-based adaptive control. So bringing that idea here, I'm sort of thinking of all the data that we get off a grid as like a picture, okay, in a movie. And then there's another picture and another picture. So if instead of looking at one bus and following its trajectory and then making some decision about what to do, we should look at a few of these pictures and get as much information as we can about how things interact with each other, and maybe we can make quicker decisions. So I got this really bright guy who just came from Tsinghua. What's his Li Pang too. And anyway, he's been working on looking for what he calls shapelets. And so what we want with these pictures coming at you is to detect motifs, if you like, in the dynamics. So he calls it shapelets. So if you can detect these shapelets, and he uses all kinds of machine learning and so on, we can get quick assessment of like voltage collapse. And now he's working with me on stability analysis. So I think there's all these papers are either appearing or to appear. He's got a paper coming up in the general meeting which he calls Photon plus 2. So in order to get a very quick assessment, he takes data points just before on the fault on, during, and then 1 point after the fault on, and then we do kind of we translate all this into an image. And so you get involved in a totally different world of stability analysis based on data, where from these images we can see the behavior of the system. That's a summary of several papers in a couple of slides, which I don't have time for. Okay, conclusions. Okay, if I had more time, I would just compare power. I still see power systems as in a simulation-based paradigm, predominantly, not people in this room, but between mathematics-based, simulation-based, and data-based, different subjects occupy different places, and I think we've got to shift a bit. The advantages of mathematics, I think Janos said most of what's in my next 2 or 3 slides, but I just make the slides will be available, but I just make my own insights into the comparison of the mathematics and computation and data-based methods. To some extent, data-based methods are a bit trendy and you can get money, but I don't believe we should just use them as a tool. A couple of my students have done things like bringing topology into data-based methods. So we can take the general idea of machine learning, but I think we can do system-specific things to improve the performance, and that makes more interesting research. Okay, but what about the future? Well, already the Chinese grid is just enormously complex. They're building markets, they're building system expansion, etc. And then here's a picture from the US where the electrical grid is embedded in all sorts of other grids. So you have to ask yourself, mathematics versus computation versus data-based methods, you know, what's going to work across that monstrous level of complexity? And we have to give data-based methods a good chance, which is another lesson in life. Because if you'd have told me 30 years ago that I'd be thinking about statistical methods and machine learning, I'd have said no way. I mean, I'm into equations and, you know, proving things, but you have to give different methods their due. So what I'd be hopeful for, though, is across these interdependent networks that Manoj mentioned, like earlier in her talk, it's very interesting, maybe some kind of hybrid technique is right. The mathematics can help produce indicators. The computation can deal with all the scenarios, and the database methods can help us learn from the past. You know, there's elements of that story coming to play, but I would just be confident that researchers have plenty to do yet, and on that note, I'll finish. Thank you.
As I said, we started a bit late, so we definitely have time for questions. In fact, what I'm going to do is, because we're running perilously close to lunch, can I take a short question from 3 people? No discussion. We're going to lob all the questions up onto in an untitled pile, and David is going to triage them for us. So, question 1.
Thank you very much for your inspiring presentation. My question is about low inertia systems. Do you think that by simulating inertia in power electronics is possible to achieve the same level of intrinsic stability that we already have using the mechanical approach of classical synchronous
Okay, so let's hold that question. Is there low energy systems?
Good question, yeah.
Well, 2 in 1. First thing is related to what the previous question is. All the stability analysis is based on the synchronous machine. As we're moving to inverter connected generators generation, that we need to maybe get away completely from the old framework and develop a new framework.
Yep.
Forget about inertia, and the synchronism. Maybe that calls for completely new.
Good.
theory.
That question's answered. Yeah.
And the last bit, which is about synchrophasor data. Well, all the traditional analysis is model-based. Maybe we should, with all the data coming from WAMs, from PMUs, I believe we should switch to the measurement-based analysis, because the model-based analysis is wrong.
So measurement, is that equivalent to database?
Because the system is changing so quickly at the moment that is completely wrong. We have to use whatever we have, which is the data.
He believes in sensors and big data. Great. So question number 2, question number 3, somewhere. Denise?
So I was actually struck when you were talking about your microgrids and that you lose stability with these radial connections. And I was thinking about distribution systems, and as we get more devices on distribution systems, because a lot of these, you know, electric vehicles and the demand, it's all dynamics on distribution systems. So you're kind of scaring me that now distribution systems are going to become fundamentally unstable because we connect them in radial connections. Is that something I should take from what you said?
Yes, yeah.
Wonderful. We've got 3 questions, great. So, would you like to?
Okay, as best as I recall, so your question, yes, of course, we can emulate inertia and scatter it around and figure out, I even got involved in a bit of that question, but the next question is, well, answered by Janusz, why should we do the old way? Maybe that's why we're working on these sort of 100% renewable type stability. Maybe all that inertia has caused some problems as well as solving problems. So if you think outside the box, and I think there's a talk later in the day about inertia. Enrique, is it? Yeah. Maybe he can answer the question. But as a person thinking outside the box, I'd say, well, before we jump into all that, maybe as an interim measure, it kind of to ease the transition. And this is one of the big things with power grids. We can easily imagine an alternative world, right? But we have to get from here to there through politicians and companies. So we have to be a bit realistic about that pathway. But from an analytical point of view, maybe inertia is overrated. I don't know. As long as we've got good control to manage it.
Is that also, I mean, is that you're answering the same, Denise's question in a different way?
No, well, I think her question's a bit different and to some extent more exciting, because there's a situation where we really take things for granted. Distribution systems, radial connections. I mean, we just think it's been around for a long time. It's not. When I was younger, that was about the most least interesting system that you could give to a researcher. Now it's where everything maybe is happening. So I think it's a really good question, and I don't have a complete answer, but our little result there shows that at least it's worth thinking about.
Great.
And
Data
was it-
analysis, you didn't answer.
Huh?
WAMS.
WAMS.
About switching
Oh,
from
well, I went too quickly at the end that I just agree with you that I'm basically, as an analyst who learned a lot of maths, I'm saying when you just look at that complexity and the fact that things are changing, so now it's changing in time from hour to hour, minute to minute, a measurement-based approach, which is kind of what the smart grids started to do at distribution level, I think that now applies to the whole system. But, you know, we have to deal with the cybersecurity issues and so on that come up. A bit like society at large, right? We're being monitored all over the place, but we have to deal with the problems arising.
Okay, with that, both present day and future way to look at things. Thank you very much, Mark.
Okay, thank you.